Alright, chemistry students, it's time to learn about electrons and atoms. How atoms behave is largely based on the behavior of electrons. And our first goal is kind of breaking apart our old idea of the Bohr model of the atom and building a more modern understanding of the atom. We call our current model the quantum mechanical model of an atom. The idea of quantum is it's a little bundle of energy. So we have a mechanical model or a motion-based model of an atom that involves little bundles of energy. In our quantum mechanical model, or the electron cloud model as it's sometimes called, the electrons aren't traveling in single straight line orbits, not like planets around the sun anymore. Instead, what we know are there are areas where electrons are likely to be found. We can't guarantee the exact position or velocity of an electron at any given moment without affecting it and altering where it is found in space. That's known as Heisenberg's uncertainty principle. If we grab it to know exactly where it is, we've messed with its velocity. And if we are measuring its velocity by observing it, we're going to alter its location. We won't know both at once, so we have a probable location for electrons, a cloud, an area where an electron is likely to be. So the idea is that we've got a nucleus that attracts electrons, and these electrons are found in very specific levels, each one getting farther from the nucleus and having a higher energy electron in each. What that means is an electron that's in level 1 is only going to be there while it's low energy. And if I give it the opportunity or the energy, it'll jump up to a higher level and to a higher level. And when it falls from one level to another, it's going to give off that energy, oftentimes as a little photon of light. But these levels aren't nice, neat little paths or rungs on a ladder or even only spheres. The levels are made up of sublevels, various electron cloud shapes that are found at a certain distance or level away from the nucleus. So within these levels are the sublevels, sometimes called orbitals. And those shapes are fairly funky looking. The s orbital is the easy one. That's a sphere, with the center of those axes there being the nucleus of the atom. Remember, a very tiny volume of the atom as a whole is the nucleus. The rest is mostly empty space. The s orbital can hold 2 electrons, one with a spin of one direction, the other with an opposing spin, so that their electrical and magnetic fields don't interact with each other negatively and boost each other right on out of the level. There is a p suborbital shape, and the orbital shapes for p are found on the x-axis, the y-axis, and the z-axis. And each of these dumbbell shapes, or teardrop shapes as they're called, will hold an electron. So on the x-axis, these p orbitals will hold 1 electron on the left and 1 on the right, and they'll move back and forth between them. Same thing with y, 2 more there and 2 more there. So the p orbitals will hold a total of 6 electrons, 2 in each of our 3 axes. The d orbitals, just another shape, a sublevel shape, are made of these kind of electron clover leaves, and kind of a funky one with a donut around the middle. And though I like donuts, I didn't try to draw these for you in class the other day. I wanted you to just kind of see how they looked with someone who has some actual artistic skill, a graphic designer. And you can see how they exist in different planes, with each lobe on the clover leaf representing a region where electrons are likely to be found. Again, each shape can only hold up to 2 electrons. So the 5 different shapes will hold a total of 10 electrons. And there are others. There are f orbitals as well, and beyond that. The complexity of the levels just keep on increasing as they go. And you can start to see why we get this electron cloud idea. If we have a sphere with another sphere layered on top of it with some dumbbells on top of that in 3 different planes, and then another sphere on top of that with 3 more axes worth of dumbbells and then some clover leaves, it starts to get pretty convoluted. We get this cloud shape going on. Can't forget the donut. We get an electron cloud in any event. So how do we keep track of all of these sublevels and levels? Well, each level has a specific number of sublevels that it can hold, based on its size. Remember, the lower sublevels are fairly small. They're closer to the nucleus. If you pack a bunch of electrons in, those electrons will repel each other right back out. Level 1 holds 1 sublevel, happens to be in the shape of an S. Level 2 will hold 2 sublevels. There's an S, and then the 3p options are available as well. Level 3 has 3 sublevels, an S, 3 Ps, and 5 Ds. You can see the pattern there. Now each sublevel can only hold 2 electrons. Any more than that, an electron gets booted out to the next available sublevel. What we're going to do is we're going to learn a method called orbital notation, a way of writing where those electrons are and representing them as arrows. Here's how it works. So what we're going to do is we're going to represent levels where electrons can be found and their sublevels. The first level is level 1. I'm going to draw a little space in level 1 to put some electrons in. Now level 1 only has an S sublevel, that sphere shape. Let's try to write this without any sort of computer malfunction. Completely impossible for me. Anyway, level 2, I'll write up here, 2, and it has an S level as well. Oh, this is getting annoying, pen. All right, let's try this again. Level 2 also has 3 P spaces that we'll call 2P. There's the X, the Y, and the Z. Level 3 has an S, has P's, and D's. And remember, there were 5 shapes for 5 D's, so I'm putting 5 spaces. And then I would like to find an element. I'd like to find an element to use for our example today. So I'm going to pick, let's pick boron. Element boron. We love boron despite its unfortunate name. It has 5 electrons. Now the electrons, as we add them, are going to fill the lowest available energy level first. So the first electron we add in for boron is going to go in its lowest space right here. The second electron we add in, represented by an arrow, I'm going to put as a downward arrow right here. It's going to take the lowest available space first. So we have 1s with 2 electrons. I'm representing them with arrows pointing in opposite directions, indicating that the electrons are oscillating in opposite directions, probably spinning in opposite directions. Now that's 2 of the electrons. The third one can't fit in the first level, so it has to jump up to the second level. 3. And then the fourth electron, 4, goes right here. I could come up to the P level, but remember how complicated those P levels looked as dumbbells compared to the sphere? They're also higher energy. The electrons will take the lowest energy available space that's open. In this case, that extra space there in the 2s level. Electron 5 will go right here in the 2p level because it's the next available lowest level. If I wanted to represent the electrons for carbon, where I was adding a 6th electron in that case, I'm going to add it right here. You may be thinking to yourself, he could have put it in the first 2p space, the 2px space, just pointed downward. But these electrons are repelling each other, and since these 2p spaces are of equal energy value, the electrons are going to choose their own space. Well, not choose. They're going to be pushed into their own space individually before they start to double up. If I want to represent the electrons for nitrogen, which have 1 more, it will go here. How about oxygen? Well, for oxygen, I have a choice. I could bump an electron up to the 3s level, but that takes more energy. The electrons are going to start doubling up. They'll only do this if the only other option is to have more energy to get up to that 3s level. And I've represented the electrons here for oxygen, fluorine, and then neon. So boron only had 5, carbon had 6, nitrogen had 7, oxygen had 8, fluorine 9, and neon has 10 electrons. You'll notice I've filled the first level with 2 electrons. Helium has 2 electrons. And I filled the second level with neon. Now there's 8 electrons plus 2 neon. If we look on the periodic table, you'll notice at the end of the first row is helium. At the end of the second row is neon. This is something that wasn't planned when the periodic table was designed, but it's a pretty great tool for us as we learn to place electrons in their various levels and sublevels, that the periodic table lines up with this. After that, we would move up to the 3s level, the 3p level, and the 3d level. So really we followed three rules there. That electrons will go to the lowest energy level available first. They'll only double up when they have to avoid going to a higher energy level. And if I have equal energy levels, they'll go single before they double up within that level. These are summaries of three rules that have names to them. The Aufbau Principle, where electrons enter orbitals of the lowest energy first. The Pauli exclusion principle, only 2 electrons per orbital. Any third one that comes in is going to be boosted up. And then Hund's rule, where electrons occupy orbitals of equal energy. They will each have their own orbital if possible. All three of these rules are in effect when we observe the behavior of electrons. These aren't rules that we've put in place and electrons are following. These are observed in the behavior of electrons. If we go back to that previous model, what I tend to keep in mind here is that these are like people, specifically guys, renting a hotel in, let's say, Vegas. They're going to choose the cheapest, the lowest energy rooms first. They'll double up if they have to, but if it comes to more than that, they're not going to share a bed. They're going to bump up to the next hotel room, even if it's a little more money, energy in this case. And if they have to, they'll go to a slightly more energetic or expensive room. But if they have their choice between sharing an expensive room or having their own expensive room, they'll choose their own if the cost is the same. They only double up when they have to. They choose the lowest possible. Since hotel rooms typically have 2 beds and guys tend to be fairly selfish, sorry, I know it's how we are, we're each going to just stick with 1 person per bed. It's probably best, really. Have you smelled a guy at a trip to Vegas? It's not pleasant. Let's skip forward before I get any weirder. So those are the 3 rules applied. There is a catch to all of this. Our order of filling kind of breaks down a bit. 4s will fill before 3d. This is because level 4 and level 3 overlap a little bit. The farther away they get from the nucleus, the more likely these electrons are to overlap with each other. Often it's just because we have so many electrons in those levels. So our order of filling gets a bit altered, and I wanted to show you a way that we can keep track of the order of filling of electrons. What I've done here is I've just written for each level all of the sublevels that are most commonly filled. 1s, 2s and 2p, 3s and 3p and 3d, 4s, 4p, 4d, and then there's a 4f sublevel. For level 5, typically s, p, d, f are filled, and for level 6, 6s and 6p are often filled. Very rarely do electrons go beyond that in their ground state. And we're going to stick with electrons that are typically in level 4 or lower. But if I follow these arrows that I'm going to draw, I'll know the order of filling. First, electrons will fill 1s, then level 2s, and then 2p, and then 3s. So far, the arrows are just going through the order we've followed. Then 3p, and then 4s before hitting 3d. This is because 4s actually dips down a little bit into the 3 level. Then electrons will fill the 3d before going back out to level 4p. And then 5s fills before 4d. Then 5p, then 6s, 4f, 5d, 6p, 5f, typically the last one full. The arrows I've drawn are just a memory trick. If we follow these arrows in order, we'll be filling the electrons in order that they actually do as they go from the ground state up.